SR latch circuit. The bistable element consisting of two cross-coupled inverters figure has two stable operating modes or states. The circuit preserves its state either one of the two possible modes as long as the power supply voltage is provided. Hence, the circuit can perform a simple memory function of holding its state. However, the simple two-inverter circuit alone has no provision for allowing its state to be changed externally from one stable operating mode to the other. To allow such change of state, we must add simple switches to the high stable element, which can be used to force or trigger the circuit from one operating point to the other. Figure shows the circuit structure of the simple CMOS SR latch, which has two such triggering inputs S set and R reset. In the literature, the SR latch is also called as SR flip-flop, since two stable states can be switched back and forth. The circuit consists of two CMOS NOR 2 gates. One of the input terminals of each NOR gate is used to cross-couple two. You can see the figure CMOS SR latch circuit based on NOR 2 gates. The output of the other NOR gate while the second input enables triggering of the circuit. The SR latch circuit has two complementary outputs, Q and Q dash. By definition, the latch is said to be in its set state when Q is equal to logic 1 and Q dash is equal to logic 0. Conversely, the latch is in its reset state when the output Q is equal to logic 0 and Q dash is equal to 1. The state level schematic of the SR latch consisting of two NOR 2 gates and the corresponding block diagram representation are shown in figure. It can easily be seen that when both input signals are equal to logic 0, the SR latch will operate exactly like simple cross-coupled bistable element explained earlier. That is, it will hold either one of its two stable operating point states as determined by the previous inputs. If the set input S is equal to logic 1 and the reset input is equal to logic 0, then the output node Q will be forced to logic 1 while the output node Q is forced to logic 0. This means that the SR latch will be set. Regardless of its previous states. Similarly, if S is equal to 0 and R is equal to 1, then the output node Q will be forced to 0 while Q dash is forced to 1. As with the input combination, the latch is reset regardless of its previous held state. Finally, consider the case in which both of the inputs S and R are equal to logic 1. In this case, the output nodes will be forced to logic 0, which conflicts with the complementary hit the complementary of Q and Q dash. Therefore, its input combination, this input combination is not permitted during normal operation and is considered to be a non-allowed condition. The truth table of NOR based SR latch is summarized in table. The operation of CMOS SR latch circuit shown in figure can be examined in more detail by considering the operating modes of the four NMOS transistors M1, M2, M3 and M4 if the set input S is equal to VOH and the reset input R is. Here you can see the truth table of NOR based SR latch. And also the table operating modes of the transistors in the NOR based CMOS SR latch circuit equal to VOL. Both of the parallel connected transistors M1 and M2 will be on. Consecutively, the voltage on node Q1 will assume a logic low level of VOL equal to 0. At the same time, both M3 and M4 are turned off, which results in a logic high voltage VOH at node Q. If the reset input R is equal to VOH and the set input S is equal to VOL, the situation will be reserved M1 and M2 turned off and M3 and M4 turned on. When both of the input voltages are equal to VOL, on the other hand, there are two possibilities depending on the previous state of the SR latch. Either M1 or M2 will be on while both of the triggered transistors M1 and M4 are off. This will generate a logic low level of VOL equal to 0 at one of the output nodes while the complementary output node is at VOH. The static operation modes and voltages levels of the NOR based CMOS SR latch circuit are summarized in the table. For simplicity, the operating modes of the complementary PMOS transistors are not explicitly listed here. For the transient analysis of SR latch circuit, we have to consider an event which results in a state change, that is either an initial reset latch being set by applying a set signal or an initial set latch being reset by applying a reset signal. In either case, we note that both of the output nodes undergo simultaneous voltage transitions. While one output is rising from its logic low level to logic high, the other output node is falling from its initial logic high level to logic low level. Thus, an interesting problem is to establish an amount of time required for the simultaneous switching of the two output nodes. The exact solution of the problem obviously requires the simultaneous solution of two coupled differential equations, one each for each output node. The problem can, however, be simplified considerably if we assume that the two events take place in sequence rather than simultaneously. This assumption causes an overestimation of the switching time. To calculate the switching times for both output nodes, we first have to find the total parasitic capacitance associated with each node. Simple inception of the circuit shows that the total lumped capacitance at each output node can be approximated as follows. CQ is equal to CGB2 plus CGB5 plus CDB3 plus CDB4 plus CDB7 plus CSB7 plus CDB8. CQ dash is equal to CGB3 plus CGB7 plus CGB1 CDB1 plus CDB2 plus CDB5 plus CSB5 plus CDB6. The circuit diagram of the SR latch is shown in figure together with the lumped load capacitances at the nodes Q and Q dash, assuming that the latch is initially reset, and circuit diagram of the CMOS SR latch showing the lumped load capacitances at both output nodes. That a set operation is being performed by applying S equal to 1 and R equal to 0, the rise time associated with node Q can be now estimated as follows. Tau rise Q SR minus latch is equal to tau rise Q node 2 plus tau fall Q dash node 2. Note that the calculation of the switching time tau rise Q requires two separate calculations for the rise and fall times of node 2 gates. It is obviously that by considering the two events separately, that is, one of the following node voltages Q dash falling from high to low due to turn on of M1, followed by the other node voltage Q rising from low to high due to turn off of M3, we are bound to overestimate the actual switching time for the SR latch. Both M2 and M4 can be assumed to be off in this process, although M2 can be turned on as Q rises, thus actually shortening the Q node fall time. This approach, however, yields a simpler first order prediction for the time delay as opposed to the simultaneous solution of two coupled differential equations. The NOR based SR latch can also be implemented by using two cross coupled depletion load and MOS NOT 2 gates as shown in figure. From the logic point of view, the operation principle of the depletion load and MOS NOR based SR latch is identical to that of CMOS SR latch. In terms of power dissipation, the noise margins, however, the CMOS circuit implementation offers a better alternative since both of the CMOS NOR 2 gates dissipate virtually no static power for preserving a state, and since output voltages can exhibit a full swing or between 0 and VDD. Now consider a different approach for building the basic SR latch circuit. Instead of using two NOR 2 gates, we can use NAND 2 gates as shown in figure. Here, one input of each NAND gate is used to cross couple to the output of the other NAND gate, while the second input enables external triggering. A close inspection of the NAND gate SR latch circuit reveals that in order to preserve a state, both of the external trigger inputs must be equal to logic 1. Here you can see the figure depletion load and MOS SR latch circuit based on NOR 2 gates. Figure CMOS SR latch circuit based on NAND 2 gates. The operating point or the state of the circuit can be changed only by pulling the set input to logic 0 by pulling the reset input to 0, we can observe that if S is equal to 0 and R is equal to 1, the output Q attains a logic 1 value and the complementary output Q becomes logic 0. Thus, in order to set the NAND SR latch, a logic 0 must be applied to the set S input. Similarly, in order to reset the latch, a logic 0 must be applied to the reset R input. The conclusion is that the NAND based SR latch responds to active low input signals as opposed to the NOR based SR latch, which responds to active high inputs. Note that if both input signals are equal to logic 0, both output nodes assume a logic high level, which is not allowed because it violates the complementary of the two outputs. The gate level schematic of the corresponding block diagram representation of the NAND based SR latch circuit are shown in figure. The small circles at the S and R input terminals indicate that the circuit responds to active low input signals. The truth table of the NAND SR latch is also shown in figure. The same approach used in the timing analysis of NOR based SR latch can be applied to NAND based SR latches. The NAND based SR latch can also be implemented by using two cross-coupled depletion load NAND gates as shown in figure. While the operating principle is identical to that of CMOS NAND SR latch, from the logic point of view, the CMOS circuit implementation again offers a better alternative in terms of static power dissipation and noise margins. As you can see, the figure, the gate level schematic and block diagram of the NAND based SR latch, figure depletion load and MOS NAND based SR latch circuit. Thank you.